Alright, by this time you've probably used the Pythagorean theorem a lot, which is if triangle if ABC is a right triangle, then a squared plus b squared equals c squared. Or in other words, um, the square of the hypotenuse of a right triangle is equal to the sum of the squares of the other two sides, right? So, um, how do we know that's true though? Well, it's been proved. In fact, it's been proved in many, many, many different ways. And in fact, if you wanted to, and if you tried hard, you could probably come up with your own proof. There's all kinds of creative ways of proving that this theorem is true. And I want to show you one of my favorites. It's very visual. That's why it's one of my favorites. So we can start with the right triangle here. I should mark that this is the right triangle, but I'm telling you it's the right triangle. Um, and we'll call the orange side. Let's call the orange side A, and we'll call the green side B, and the other side will be C, the hypotenuse. All right, well check this out. We can copy this and rotate it and form a new shape here. So I'm just keeping the exact same triangle and copying it and rotating it 4 times. Right, so rotating, yeah, like that. Okay, so when we do that, we get this awesome square, which is missing a square on the inside. All right, so let's see here. So what we can do is we can write the area of the square in 2 different ways. Okay, so the area of a square is just its side squared, right? Okay, so what is the actual side length of the big square? Well, this is b plus um, a, right? And each side is b plus a, b plus a, b plus a, right? So the area of the big square is b plus a squared. Agreed? Well, what's another way of writing the area of the big square? Well, we've got 4 different triangles, and then we've got this square in the middle. So what we could do is we could take the area of one of these triangles, multiply by 4 to get the 4 triangles, and then figure out the area of the square and add that, and then we get the total area. So the area of one triangle, so the area of a triangle is 1/2 base times height. So for a right triangle, um, you know, you could call A the base and B the height, or B the base and A the height. Doesn't matter. So we'll do 1/2. Let's call B the base, and then A will therefore be the height. So 1/2 B times A, and we're gonna multiply that by 4 to get all 4 triangles. Multiply that by 4, and then we're gonna add on the area of this square. Well, what is the area of that square? Well, this side length is C. That's C. That's C. C, right? That's the hypotenuse of these triangles. So the area of that square is just C squared. Yeah? C times C will give us the area of that square. Then we'll add it to 4 times the area of these triangles. Alright, so if we can simplify this and get a squared plus b squared equals c squared, we have proved the theorem. So b plus a squared, let's see, I need to get myself some room here to write. So I'm going to b plus a squared, we'll just distribute that, FOIL that, b plus a, b plus a. So b times b is b squared. B times a is BA, but I'm going to write it as AB, so it's alphabetical order, and so it's the same as this. A times B is AB, as I see, and then I can combine like terms. And a plus a is a squared. So b squared plus 2ab plus a squared would be this side. 4 times 1/2 ab would just be 2, or sorry, ba. I'm gonna just flip those around. Just call them ab, so it's clear that they match up here. So it's 2ab plus c squared. So this is equal to 2ab plus c squared. Now subtract 2ab from both sides of the equation. 2ab minus 2ab. 2ab is gone, 2ab is gone, so all we have left is b squared plus a squared, but I'm going to write it in a different order, a squared plus b squared, because it doesn't matter the order in which you add things, equals, all that's left there is c squared. There you go. So yeah, pretty cool proof, right? It's very visual. So think of a way that you could prove the Pythagorean theorem, and it's fun, hard but fun. All right, that's it.